All right, so just a second ago, I told you that checking linear independence is going to be important for us knowing when we have solutions. And the easiest way is going to be using this Wronskian. But I want to make sure that we know how to use that thing. So we're going to do a quick example where we kind of show that some functions are linearly independent. So we're going to be thinking about the differential equation y double prime minus 9y equal to 0. And we're going to think about y1 equal to e to the 3x and y2 equal to e to the minus 3x. These two things are solutions to that differential equation, and you'll learn how to find that out later. But right now we could just sort of check that they are solutions. So actually I'll do little arrows so you can kind of keep everything separated. So they do satisfy the ODE. That means they are solutions. And you can do that real easy. y1 is e to the 3x. So y1 prime is 3 e to the 3x. And y1 double prime is 9 e to the 3x. So when you take y1 double prime minus 9y1, you get you get 9e to the 3x minus 9e to the 3x. Which is 0. And the same thing is going to happen with e to the minus 3x because of negatives multiplying together, but we'll do it real quick. y2 is e to the minus 3x. So y2 prime is minus 3 e to the minus 3x. And y2 double prime is minus 3 times minus 3 is 9 e to the minus 3x. So then y2 double prime minus 9 y2 is going to be 9 e to the minus 3x, where I was plugging in y2 double prime, which we calculated right there, minus 9 e to the minus 3x, where I was plugging in y2, which was e to the minus 3x. And that's 0. So both of these functions that I told you are solutions to the differential equation are solutions to the differential equation. And then I said linear independence first, but I'm going to check that I have the correct number first because it's easier. So I have two functions, y1, y2. The differential equation is second order. Y double prime minus 9y equals 0. That double prime means that I have second order. So I have the correct number of solutions. And so my last thing that I have to check is whether the solutions are linearly independent. And so I do that by calculating my Wronskian, which I said is a determinant. We'll worry about what that means in a second. But I said you put your y's on the top row, and then you take derivatives down until you have a square shape. So since I have two solutions going this way, I have to make sure I have two derivatives going down. That's what I mean by a square shape. You have as many rows as you have columns. So my first row is y1, y2, 2 columns. That means I need 2 rows. So I just go down taking derivatives. But I already know what y1 and y2 are. They're e to the 3x and e to the minus 3x. And I took their derivatives right here, so I can go ahead and say y1 prime is 3 e to the 3x. Y2 prime is minus 3 e to the minus 3x. That's how I fill up my Wronskian. And then the second part of this is that the Wronskian is taking a determinant. So when you take a determinant, this should be review for you, but all you do is you multiply across the diagonal and then subtract multiplication from the off diagonal. That's how you take a determinant. If your W is bigger than that, the determinant is harder to take, but we'll cross that bridge later. So for us, it's going to be this product. So e to the 3x times minus 3 e to the minus 3x minus, minus this product, e to the minus 3x times 3 e to the 3x. And when I multiply e to the minus 3x, oops, this was e plus 3x. When I multiply e to the minus 3x by e to the 3x, those negative and positive exponents cancel out to just e to the 0. So I've got minus 3 e to the 0 minus 3 e to the 0. It's just minus 3 is minus 6. And really the number that the Wronskian gives you doesn't matter except that it's not 0. So since I didn't get 0, I know that y1 and y2 are linearly independent. And so that's that second special property that two solutions have to have in order to form a general solution. And so that brings us to sort of the purpose of why we introduced this idea of wanting to solve an nth order differential equation and sort of talked about these two important properties is because in order to write the general solution to an nth order ODE, sort of if you have y1, y2 down through yn, form something we'll call a fundamental solution set. Which is going to just mean that they satisfy those special properties that we said matter. So that's going to be that, oh, no, get away from there. Y1 through yn are solutions. To the ODE. That you have n of them. For nth order ODE. And that they're linearly independent. Or in shorthand, we're going to say that the Wronskian is non-zero. Then if those special properties are met, the general solution to a homogeneous nth order ODE given by that star is going to be y equal to c1 y1 plus c2 y2 all the way down through cn yn. And those c's are unknown constants that we have to solve for in an initial value problem. So for like this example right here, sort of we could finish by saying y equal to c1 e to the 3x plus c2 e to the minus 3x is the general solution. Oh, that star is a bad thing to use because that's how I'm labeling things. So we'll just put it in a little box. So the reason we checked those three properties is because they tell us that we can build a general solution in this way. And we'll address that non-homogeneous equation next.